Welcome, everyone. So glad you're joining us for this explainer. Today, we are tackling a massive fundamental topic, our home planet. We're going to dive deep into geology, which I honestly like to think of as Earth's body science. Think about it. Just like a doctor studies the human body to understand how it functions, we are going to study the Earth's body, its rocks, its mountains, its deep, boiling interior. We're going to figure out how our environment actually works and how we interact with it every single day. To make sure we don't get totally lost in 4.6 billion years of history, here's our roadmap for today. We'll start by looking at Earth as a closed spaceship. Then, we'll peel back the layers inside the onion, check out Earth's recycling program, and finish up with the epic battle between the builders and the destroyers. Let's get right into it. Section 1. Earth, a closed spaceship. Before we even touch a single rock, we've got to understand the rules of the game here. I want you to think about this question. What actually happens when you throw garbage away on a spaceship? I mean, you can't exactly roll down the window and toss it out, right? Well, Earth is exactly like a giant sealed spaceship, just hurtling through the void. Sure, we get a constant stream of sunlight and heat from the sun, so energy comes in, but absolutely zero new physical matter enters from space, and nothing leaves. This beautifully illustrates what we call a closed system. We trade energy with space, but definitely not matter. Think about the reality of that for a second. Every single drop of water you drink, every atom of carbon, every molecule of nitrogen we have right now is just being endlessly recycled. So when we produce waste or pump out pollution or dump plastic, it doesn't disappear. Actually, scratch that. It can't disappear. It just changes form and moves somewhere else. On a closed spaceship, there literally is no such thing as away. Section 2. Inside the onion. All right, so we've got our spaceship rules down. Now let's crack open Earth's history book, the geological timescale, to see how it's built. We're going to zoom way in on the most recent chapter, the Phanerozoic Eon. This is where all the complex, visible life happens, and it's split into three main eras. First up, the Paleozoic, kicking off about 540 million years ago. This brought us the very first fish, plants, and insects. Then we hit the Mesozoic, which you probably know as the age of dinosaurs. And finally, after that massive asteroid crashed the party 66 million years ago, we entered the Cenozoic, the age of mammals. That's us. So how do these billions of years physically build our planet? Picture Earth like a giant onion. On the very outside, you have the crust. It is crazy thin, only about 5 to 70 kilometers thick. It's basically just the skin of an apple. Below that sits the mantle, a massive 2,900-kilometer layer of thick, slowly flowing solid rock. Go deeper, and you hit the outer core. This is a 4,500-degree churning ocean of liquid iron and nickel. And get this, that liquid metal actually generates the magnetic field that protects our whole spaceship from deadly solar radiation. Finally, dead center is the inner core. It's scorching hot, 5,500 degrees, basically as hot as the surface of the sun, but the pressure down there is so intense that the iron and nickel are literally crushed into a solid ball. Now, what's really wild is what that incredibly thin crust we live on is actually made of. A massive 47% of our solid ground is oxygen. I know, we usually think of oxygen as that invisible gas we breathe, but down there, it's locked up tight. It combines with elements like silicon and aluminum to physically build rocks. Under the oceans, these elements form dark, heavy basalt, and under our feet on the continents, they form the lighter granite that builds our land masses. Moving on to Section 3, Earth's recycling program. Okay, we've got our ingredients, so how does Earth cook with them? Remember that closed system we talked about? Well, rocks get recycled just like everything else. It's nature's ultimate recycling program, the rock cycle, and it takes millions of years. It all starts with super hot magma cooling down to form igneous rock. Think of the solid granite in a kitchen countertop. Over time, weather beats up that granite, breaking it into tiny pieces that wash away, pile up, and compress into sedimentary rock, kind of like limestone used in cement. Now, if you take that limestone, bury it deep underground, and crank up the heat and pressure, it literally bakes and morphs into metamorphic rock. That's how we get things like beautiful marble statues. But what's actually driving this endless recycling loop? Well, it's basically an epic, multi-billion-year battle between two opposing forces. In one corner, we have endogenic forces. Let's call them the builders. These are constructive forces pushing outward from deep inside the planet. In the other corner, we have exogenic forces. Let's call them the destroyers. These are the outside forces constantly trying to wear the Earth right back down. Let's meet the first group in Section 4, the builders, internal forces. All right, time to meet the builders. These are those dramatic endogenic processes, and they are entirely powered by all that intense heat trying to escape from Earth's core. This heat makes the mantle churn and boil, kind of like a thick soup on a stove. Those slow convection currents drag massive tectonic plates all around the globe. When these plates pull apart at divergent boundaries, like the Mid-Atlantic Ridge, brand new crust is born. When they scrape past each other at transform boundaries, like the famous San Andreas Fault, they build up massive friction. And when they slam head-on at convergent boundaries, they build mountains. Seriously, right now, the Indian plate is crashing into the Asian plate, and it's pushing the Himalayas up by a whopping 5 centimeters every single year. That very same internal heat is also what gives us volcanoes. And they actually come in a few different flavors depending on how they erupt. Shield volcanoes, like the ones in Hawaii, have these really gentle slopes built by slow oozing lava. But stratovolcanoes, like Mount Fuji, those are the tall, highly explosive ones, and they pose incredible hazards to the environment. The absolute scariest part is the pyroclastic flow. Imagine a 700-degree avalanche of ash, gas, and rock just racing down the mountain, followed by terrifying, fast-moving mud flows called lahars that can literally wipe out entire river valleys in minutes. As these massive plates grind against each other, we get our next builder, earthquakes. You can understand this using the elastic rebound theory. It's just like bending a wooden stick. You bend it, tension builds up, and then snap. The rocks break and violently snap back into place. The exact spot deep underground where that snap happens is called the focus, and the spot on the surface directly above it is the epicenter. Now that snap sends out shockwaves, and here's a super cool fact. One type, called S-waves, ripple like a wavy rope and can only travel through solids. Because those S-waves get completely blocked by the center of the Earth, geologists were able to prove without a doubt that the Earth's outer core is entirely liquid. How wild is that? So how do we measure the sheer power of that snap? We use the Richter scale. But here's the thing you have to know. The Richter scale is logarithmic, which means it is highly, highly deceptive. If an earthquake goes up just one whole number on the scale, the physical shaking you feel gets 10 times stronger. But keep this number in your head, 32. For every single whole number you go up on the Richter scale, the actual earthquake releases 32 times more energy. Let that sink in for a second. Okay, time to meet the opposition. Section 5, the destroyers, external forces. While the builders are busy pushing mountains up, the destroyers immediately go to work tearing them right back down. And they are powered by the sun, gravity, wind, water, and ice. Wind acts just like a giant sandblaster, constantly scraping rocks away and building massive desert dunes. Glaciers? They are basically unbelievably heavy, slow-moving rivers of ice that literally grind entire mountains down and pluck out massive U-shaped valleys. But the absolute, undisputed king of erosion is water. Over millions of years, water chemically dissolves solid limestone to carve out sprawling underground cave systems, and it physically cuts through rock to create absolute marvels like the Grand Canyon. And backing all of this up is the ultimate equalizer, gravity. Gravity drives what geologists call mass wasting, which is just the downhill movement of Earth. Sometimes it's a creep, this almost invisible process that slowly tilts fences over decades. Other times, it is a terrifyingly fast debris flow or avalanche. These disasters are usually triggered by heavy rain, earthquakes, or humans cutting down forests. This is absolutely critical to understand today. Take a country like Nepal. With its steep, growing mountains and intense monsoon rains, it is incredibly vulnerable to landslides. But because we understand this geology, we can adapt. We can avoid building on steep slopes, we can construct retaining walls, and we can plant trees, because their root systems literally act like a net to bind the soil together. As we wrap up this explainer, I really want to bring us full circle. We've seen how the Earth dynamically builds itself up from the inside, only to be worn right back down from the outside. We've seen how every single rock, every drop of water, and every element is perfectly recycled in an endless loop. And that brings us right back to our spaceship. We cannot throw things away. There is no away on a closed system. Everything we dig up, everything we manufacture, and everything we toss in the trash stays right here in the Earth's body. So knowing all that, what are you going to do with your space on the ship today?